Here we are. So in this lecture, essentially, we will talk about shielding, shielding of photons, because we are still talking about photons here. So what does shielding mean? Shielding essentially means that you have a given number n0 of particles in front of your material, and then you have n particles on the other side. This is, as you know, is regulated by the most famous formula in physics, that is the exponential physics, the exponential formula, I'm sorry, the Lambert-Beer formula, if you want. And this comes from this simple observation that the decrease in the number of particles is proportional to the number of particles itself and to the thickness that you are traversing. The proportionality factor is this mu, and this is an absorption coefficient. This is called the absorption coefficient. So generally, every time you deal with photons, doesn't matter if it is radio waves, terahertz, microwaves, light, UV, or X-rays or gamma rays, the absorption is described by this kind of formula, n equal n0 e to minus mu x, that comes from the solution of this very simple differential equation of the first degree. Actually, it is much more common in our field to express this with the mass absorption coefficient, which is the ratio between the absorption coefficient and the density of the material. The unit will be square centimeter divided by grams. And then the formula will look like this one, n equal n0 e to minus mass absorption coefficient time mass thickness, where the mass thickness in grams per square centimeter is the product of the density times the thickness of the material in centimeter. Generally speaking, it is also common to have this quantity. You can define if rho and A divided by A, you see where rho is the density and A is the Avogadro number and A is the mass number. Then if you look at the units, this number, rho and A divided by A, gives you the atoms per cubic centimeter. Because you see, density is grams per cubic centimeter, Avogadro number is atoms per mole, and the mass number is grams per mole. So eventually you come out with the atoms per cubic centimeter. And sigma, the so-called cross-section, is actually given by the product of the mass absorption coefficient times Na divided by A. The dimension of this quantity, you see, square centimeter, and is known as cross-section, which is one of the most common quantities in physics, and is essentially the product of an area times a probability, because you see, area is square centimeter, probability is dimensionless, and the meaning is that a given cross-section gives you the area of the sensitive target times the probability that the photon or the particle going that sensitive target will induce a given reaction. Other important definition that you have to remember is the mean-free path. The mean-free path is actually the inverse of the absorption coefficient, so it's expressed in centimeter, and gives you essentially the mean distance between two interactions. And if you make a product between lambda and x, you have the number of mean-free paths. So how many mean-free paths you will have in a given material, and is generally expressed in MFP. So this is the number of mean-free paths. Okay, now, the absorption coefficient for the photons as a function of the photon energy is given by this famous plot. You see, the absorption coefficient or the cross-section. You see, the absorption coefficient is essentially proportional to the cross-section. It's the same thing because this is a constant. I mean, it only depends on the mass of the material. But for the Compton effect here in green, for the photoelectric effect here in green, it is quite high at low energy. You know, when you are in the energy of the atomic gaps in the atom, so it's the shells, is the atomic shells essentially, and then drops quite quickly, while the Compton effect, you see, goes up at low energy and reach a maximum here, exactly in the region that we are particularly interested in. You see, in the order of, this is kilo electron volt. You see, this is the region of the mega electron volt, and the kilo electron volt where we are particularly interested in. And finally, you have the pair production here that has a threshold, of course, as we saw already last time, and then goes up and is only important at very, very high energy. This is in water. This is the situation that we have in water. So if you look at now from the medical physics point of view, the difference, the impact of which kind of energy we are using is very big. For example, if we take a radiography, you see, if you do a radiography with the low energy X-ray, so essentially if you use X-ray in this region here, a few kilo electron volt, you are using mostly the photoelectric effect, and you will have this kind of image. You see, the photons are completely absorbed in the bone that has more density, and they are only a little bit absorbed in the muscles, you know, that you see that kind of whitish. On the other hand, if instead you move and you go in this region here where you have a prevalence of Compton effect, this is how your image will look like. Of course, the high density material here, the Compton, will appear much more white because you will have a lot of scattering of the photons on the material, while the muscles will appear much more black because now you have not so much absorption of the photons in the muscle. So you see, playing with the energy of the photons, this we will see when we will do the imaging lectures, you can actually substantially change the power of your imaging device. Now, these are useful for the exercises. You know, these are examples of attenuation coefficients for different materials. You see, like hydrogen, water vapor, air, fat, ice, water, and compact bone. You see that for compact bone, that is the effective atomic number is 13.8, and the density is 1.85. The absorption coefficient at 50 kilovolt, of course, as we have seen, this is strongly energy dependent, but you see at 50 kilovolt, the absorption coefficient is about 0.5. If you take at the same energy the absorption coefficient of the fat tissue, for example, which is close to the bone, the value is only 0.19, and water, which is very much common in our bodies, 0.2. Okay, so this is these are the attenuation coefficient that you have to use to solve the exercises if you want to find the transmission. Now, for shielding, now we have discussed, I mean, we have seen this exponential formula for one single material. Now we saw that it's an exponential decay, e to minus mu x. What happens if instead you have layered material? This is actually quite common, you know, it's very common in practice that you have different materials. You know, you have you can have concrete in a wall, you can have concrete, but you can have then lead if you want to increase the shielding, you can have plastics, you can have all kinds of material. Well, the solution is quite simple, because you see the rate, this is X point is the exposure rate. If you remember, the exposure is the Coulomb per kilogram of Röntgen, so it's the charge produced per kilogram, and this is dx on dt, so it's the rate of exposure. But of course, the same formula applies to the dose rate, to everything you want. The important thing is that simply is additive, you see, so in the exponential, of course. So you will have minus mu1 divided by rho1 times rho1 x1 plus mu2 divided by rho2 times rho2 x2. So when you know the mass absorption coefficient of the material, and you know the thickness, you can easily calculate what is the dose on this side when you are on this side, which is what in medical physics you want to know, because you want to protect. Imagine that you have a dentist praxis, and you have your X-ray machine. You turn your X-ray machine on, but there are the other patients waiting on the other side, sitting there. You want to make sure that the dose on the other side of the wall is low enough. We will see what does it mean low enough. There are laws, of course, that regulate that. But then you will have to use this formula quite massively. Now, generally, instead of using attenuation coefficient, it is more convenient to use the so-called half value layers. Sometimes people also use 10th value layers. Essentially, a half value layers, as is written, you see on the slide, is the thickness of material that reduce the radiation intensity by 1/2. Very simple, very simple. Now, of course, if you remember the definition, let's say, of exponential curve, you will come out with, say, that half value is nothing else than 0.693 divided by mu, or if you prefer, 0.693 divided by the mass attenuation coefficient times the density. So at this point, you can use this formula, where essentially you only need to know the thickness of the material and the half value layer. So the half value layer is, you find them in tables, and then once you know the half value layer, you multiply times the density, the thickness, and you find the formula for the attenuation of the beam. If instead you prefer to use the 10th value layer, this is fine, then you will end up with this formula. It's the same story, of course, but then you will have 2.3 divided by mu, and the formula here will be e2 minus 2.3 divided TVL times x, or 0.1 for the number with the exponent of the number of 10th value layers. So how many 10th value layers you have? So let's see some example here. For example, half value layers. So this table gives an idea of the approximately half value layer thickness of several shielding materials. Save this table because it's very useful for the Übungen. You see, because you have different energies. These are generic photons, 0.5, 1, 1.52. These are specific radionuclides, iridium-192, which is used in nuclear medicine, cesium-137, that is a standard for gamma rays, cobalt-60, that is even more standard for gamma rays, and radium-200 and radium-226, which is also an alpha emitter, but is also a gamma emitter. So you see the half value layers are given here for different, this is in centimeter, for uranium, tungsten, lead. These in parentheses are the 10th value layers for lead, for iron, for concrete. Keep in mind that lead, iron, concrete, and water are probably the most common that you will face, because of course concrete is everywhere. When you have shielding, you almost always have concrete because you have walls. And then you generally use high density material for shielding photons, like lead and iron. And then of course you have water in the body. So if you want to know how it is absorbed in the body in comparison the skin dose to the bone marrow dose, for example, then you will have to use the alpha value layer for water. Of course, and this makes sense, I think, to you already now, if you increase the energy of the photons, the half value layer correspondingly increase. So it's easier, of course, to shield low energy photons than high energy photons. This also, I think, makes perfectly sense. Let's make some example now. So as you see, we will now use the unit of exposure rate in Röntgen per hour. This is an old unit, but it's still very much used. I should use Coulomb per kilogram, but let me use Röntgen per hour. So let's say that the exposure rate is 100 Röntgen per hour due to a cesium-137 source. Now the question is, what will be what would be the exposure rate if the source were shielded with 2 centimeters of lead? This is a typical medical physics problem, really a classical, you know, one of those that if you want to do this work, you do it almost automatically. So what do you have to look at now? You have to look at the half value layer of lead. And you see that if you go back here for, for the cesium-137, the half value layer for lead is 0.65 centimeter. So you can easily write that this is 100 Röntgen per hour, which is my source, times e to minus 0.693, that is our constant, divided by 0.65 times 2, because it's 2 centimeters of lead. And then the new exposure rate is 12 Röntgen per hour. So you see, with 2 centimeters of lead, I go from 100 Röntgen per hour to 12 Röntgen per hour. That's not enough for radiation protection. Then I have to know how long time people stay in that room, you know, because I have to make sure that the Röntgen, or if you prefer the gray, I mean, the total dose is low enough. But that's to show you how easy are these calculations. They're really extremely simple. Unfortunately, though, they are not so simple. They are not so simple because you have a factor which is called the build-up factor. What is the build-up factor? You know, in Compton scattering, you see, only for pencil beams, if you have a pencil beam, so not a large source, but a pencil beam, every scattered photon is removed from the beam. You see, this is a situation like this, where you have a pencil beam, a very, very narrow entrance here. Then every time you have a scattered photon, it is removed from the beam. And if you have a detector here, you take only the non-scattered part. So here, the Lambert-Beer formula works fine, works perfectly. But when you go in broad beam geometry, like here, where you have a source, you know, and the source is hitting at different angles, I don't know, I don't know if you see me. Do you see me?
Yes, we do.
Yes, we see you.
Ah, you see me. Okay, I just want to make sure, because sometimes the hands, my movement of the hands can be important, you know. So when you are in broad beam situation, where you see here in this figure, in the beam, in the B, where they go a little bit everywhere, you see the photons, they scatter at an angle. In this case, what happens? Then you have those that are scattered away, fine, you know, like this one, this is going away, good. But you can have the opposite. You can have scattering. Oh my God. Now I'm sure someone will criticize, but this is not my fault. This is now the computer. And if I turn it off, you will not hear me. So I'm sorry. So you see what happens. It happens that you have scattering inside, and then the intensity is increased compared to what you would expect in a narrow beam geometry. Because now you have scattering that is not removing from the beam. It's actually bringing the photons back in the beam. So for this reason, you define the build-up factor B in this formula. You see, so the build-up factor is a function of the energy and of the thickness, and is the integral of the flux in the E divided by the integral of the flux 0 in the E. So you can also see it here. You see, this is the photon intensity. This is the length of travel. The theoretical decrease is given by this curve, the one on the bottom, but the actual decrease is given by this curve. So it's less decrease than you expect. And this difference here is the build-up factor. So the ratio, if you want, of this fluxes is the build-up factor that you have to implement to have a correct calculation of the efficacy of shielding. So you see, these are examples now of sample build-up. Material is lead. The energy, for example, you can say if the energy is 1.0, you see that the build-up factors you see here can be 1.69 or 2.26. So in an example, let's make an example. Let's say that you have an exposure rate at a particular point is 100 Röntgen per hour, and this comes from a gamma ray source of 1.3 MeV. 1.3 MeV is approximately a cobalt 60 source. What will be the resulting exposure rate if a 1 centimeter lead shield were employed between the source and the point? Assume poor geometry. Poor geometry significa broad beam geometry. Broad beam and thick shield. So now, if you take the lead, the mass attenuation coefficient is 0.057 centimeter per gram. This probably you can see it here. This is the half value layers. I think I also had a table. Yeah, I also have a table with the attenuation coefficient, but not for lead here. I'm sorry, but you can see it from the half value layers, of course. So this is approximately 0.057 centimeter square per gram, and the density of the lead is 11.35 grams per cubic centimeters. One of the highest density in nature is the lead. Now B is estimated to be 1.2 based on an energy of 1.332 MeV and a value of 0.647 for the number of framing paths. So this is probably clear here. So it says 1.2 for lead because the energy is approximately here is approximately 1 MeV, somewhere in the order of 1 MeV, and the number of mean free path is less than 1. You see, the number of mean free path is only 0.647. So it's a little bit, I'm sorry, it's not here, it's a little bit lower than this one. So you see, at one number MFP, let's say at 1 MFP, you will have 1.37. But since you have here 0.647, you only have 1.2. So the build-up factor is 1.2. And now it's very easy, of course, because now you see the solution here. You have always the same formula, but now you have to introduce the build-up factor. And then now you start from 100 Röntgen per hour, and you end up at 63 Röntgen per hour. Okay? Any questions so far? I hope you're still there because of the privacy issue. I'm trying not to see your, but I hope you are still there. I don't see faces. I only see, I see Niccolò, only Niccolò, and I hope it is clear. Any questions? Not really. Okay. So On the other hand, we can now try to estimate the thickness with the build-up factor. So what happens now? Of course, the problem can be opposite. Can be said, okay, I measure radiation here in this point in my room. Then I measure radiation, and I have a source in my rooms. Things that I don't recommend. Don't get me wrong, but let's say that I have a cobalt in my office. Then this is emitting radiation. Then I have a shield, and then I have another room. What happens in the other room? I can calculate the thickness by inverting this formula. By nothing else than doing an inversion of this formula. No, I have this formula, I have to invert. Apparently is easy, but the problem is that the build-up factor, as we have seen, is a function of the energy and of the number of mean-free paths. So this equation is not an analytic solution and would require iteration methods or Monte Carlo. So it's not possible to solve it without iteration methods or Monte Carlo, or if you are really lazy like me, just take the transmission curves that you can, for example, get from the ICRP publication 21, 1971. This is a beautiful one. And here you get the transmission factor F, you see, for this is the case of lead, this is the shielding barrier, and this is the transmission factor for cesium, for iodine, and for palladium. And the formula is this one. D star is the desired value behind shielding. That can be dose rate, can be exposure rate, whatever you are using in radiation protection. D is the distance from the point source in mean-free path, in number of mean-free path. Du is the value of the radioprotection quantity at one distance. U is the utilization factor, and T is the occupation factor. This is very important because U tells you how much you use the source, and T tells you how long you stay in that place. At the end, you come out with this formula for the transmission factor, and that's the dependence on the shielding for different energies. Unfortunately, now I gotta go. So I'm really sorry, but as I told you before, I have a little problem today, and I have to attend the meeting. I don't know if there are not many students today, though. I know Marietta is here. Less students than last time. I already managed to scare many students. So anyway, I will upload this registration. Let me stop it now.